In this video, we are given a cantilever beam that is having a varying distributed load, and the guiding question says, given a cantilever beam loaded as below, determine the internal forces at point C. So we are required to determine the internal forces, that is the bending moment and shear force plus normal force at point C. So we need the bending moment, we need the shear force, and we need the actual. Okay, we have the distributed load as 270 Newton per meter. This is a cantilever beam with support at A. The other end is free. In other words, we have an exposed end away from this support, and it is carrying a load that is varying from 270 to 0 at B, and the point C is at 3 meters from point A and 6 meters from point B. Now we need to find the external forces, and getting the external forces, we need to look at the free body diagram of this particular loading condition. When we are to calculate the total force that comes from the distributed load, it is 1215 newtons, and this is where it comes from. We know it is the distributed load is in form of a triangle, and therefore that force is always equal to the area under the distributed load area, and so this will be a half base. Of course, a half base is 9 meters, then height is 270 Newton per meter. So times the base, which is 9, times 270. So this would give you, of course, 135 times 9, and this should give you 12 Newton. Okay, so that force acts at a distance. It acts at a distance equivalent to a third of the total length. So it will act at a distance equal to 3 meters. So we realize that point C is at a distance 3 meters, and that's where that particular force is going to be acting. Now, when we have defined how to calculate for this force 1215 newtons, we have given the external forces. A cantilever beam has got a force, a reaction in the horizontal direction, a reaction in the upward direction, but also it has what we call a reactionary moment, and it is MA. So the external forces will include the reactionary moment at A, then AY, AX in the horizontal direction, and 1215 newtons acting at point C vertically downwards. So considering the free body diagram, we need to apply equilibrium conditions. Sum of forces in the horizontal direction, taking the positive x direction forces to be positive, then we will have a force AX that acts in the horizontal direction, and that AX is equal to 0. Then sum of forces in the y direction, taking the positive y direction forces to be positive, then we will have AY, which faces vertically upwards, then minus 1215, this is equal to 0, and our AY, the reaction at A vertically upwards, is 1215 newtons. Then we need to also determine the moment at A, that reactionary moment. We get it from the third equilibrium condition, which is the sum of moments about a point must equal to 0, and taking clockwise moments to be positive, then we will have negative MA, since MA acts in the negative direction or anti-clockwise direction. Then that negative MA, we add there 1215 times the perpendicular distance from point A. Of course, from point A, and therefore we will have a value equivalent to 36.45 Newton meter. Okay, having determined that MA and the rest of the external forces, then we need to make a cut or a section. So that cut section make a cut at C. So if we make a cut at C, we will realize that we will have the free body diagram. This one is AX, which is equal to 0. Then we have AY, which is 1215 newtons. Then the reactionary moment, which is 36.45 Newton meter. Then if we create a section here or a cut, we will have the shear force being V, and we will be pointing vertically downwards. If it points vertically downwards, then the moment, the bending moment, to counteract it will move in an anti-clockwise direction. Then with the new normal force N coming out of this section, and then of course having had x equal to 0, this N will also equal to 0. Then remember, this results into a trapezium. So if it is a trapezium, it means we can still break it into two figures, one a rectangle and a triangle. Now the force due to the triangle is going to be F1, that is going to act at a third of the distance from here to there. So if it is from here to there, it will be 1 meter. Then F2 will also act at a distance which is halfway, because we will have now the uniformly distributed rod portion from this point to this portion, then to this point, then moving across. Now our task is to define W Newton per meter, which is the rod that is going to be at this point. So using similarity of triangles, we can say here we have a magnitude of 270, here we have a magnitude of W. We know the distance from here to there as 9, and the distance from here to here as 6. Therefore, using the similarity of triangles, we are able to get W as 180 newtons per meter. So when we get 180 newtons per meter and we put it on our free body diagram, remember this is a zero force, and we have a shear force here, normal force, then the bending moment. So that W is 180 Newton meter. Our task now is to calculate for F1. F1 is equal to a half base height. We said this is a triangle, so the area under the triangle will give us the total force that will act at a third from this point, but 2/3 from point C. Now that will be a half times base is 3 meters, then height will be, we have already known that from here to here is 180, from here to here is 180 newtons, and from here to here is 270 newtons per meter. Therefore, to get this portion, the height, it will be 270 minus 180, and this will be in total 135 newtons, because this will be 90 times 3, that will be 270, and 270 will give you 270 half times a half will give you 135 newtons, and it will act at a distance that is equivalent to 2/3 from point C, 2/3 of 3 from point C, which will give you 2 meters, because we are looking at the distance from point C, since that's where we are going to take our moment from. Then F2 is a uniformly distributed load, so it will come from area of a rectangle. The length is 3 meters and the width is 180. So I will just get 180. This is we are saying this is width times length, and this gives us 550 newtons because it's 180 times 3, and this will act at the center from at the center of this free body diagram, and therefore since it is equal to 3, then it will be 1.5 meters from point C. Now, having known those forces, then we have determined the external forces, so we need to determine the internal forces, the shear force, the axial force, and the bending moment. Now, axial force is determined from sum of horizontal forces equal to 0, that n is already equal to 0. Shear force is determined from the summation of forces in the vertical direction being equal to 0, then taking the positive y direction forces to be positive, then 1215 acts in the positive y direction, minus v, which points vertically downwards, minus 540, minus 135, all these two forces act vertically downwards, and therefore if I subtract and make v the subject, I will have the shear force at that point equaling to 540 newtons. What about the bending moment? The bending moment, already sum of moments about that particular point must equal to 0. So if we consider point C and take clockwise moments to be positive, then I have the reactionary moment which is acting in an anti-clockwise direction, so I'll have negative 3645, then minus 540. It is also acting in an anti-clockwise direction at a distance 1.5 meters from C, so it will be minus 540 times 1.5, then minus 135, which also acts at a distance 2 meters from point C, then minus that moment M, which is also in an anti-clockwise direction, then plus the 1215, which is the reaction at point A, this is the one I'm talking about, and therefore it will remove a moment. It will have a moment about C equivalent to 1215 times 3 meters, and finally the bending moment will give us negative 180 newtons. Thank you so much. Join us in the next video when we will look at the bending moment diagram and shear force diagram for this particular problem. We have determined the internal forces, and that is the bending moment, the shear force, and the axial force, which is acting normally to the cross section of the beam.